The purpose of this lab was to analyze and track the motion of an object oscillating on a spring. We then used VPython to create a model that incorporated Newton's second law and other motion force principles. Then we plotted all the change in energies to verify the energy principle was satisfied. Then we compared and contrasted our experimental data to our model in order to look at the accuracy. Here is the video that we were given in our lecture, where a mass of 0.402 kilograms was attached to a spring. The initial position is shown, and the object started at rest. The length was measured of the spring with the mass attached. The stiffness of the spring and the L0 were calculated, which we'll look at in a later slide. When we compare the x value oscillations to the y value oscillations, we see that the x had a larger time frame between periods and was also very consistent in those time frames. The y values were measured as well from crest to crest, and we can see that the oscillations were going at a faster rate and were also much more inconsistent. This matches with what we see in the video, and that the y range of motion is much wider and less consistent than our x range, which simply goes back and forth. In order to calculate the spring stiffness and the L0, we used data from an earlier lecture in which the spring's motion was only along the y-axis. We used the period of this data to calculate the spring stiffness. Then, by saying that the constant motion meant the forces must all cancel each other out, we knew that the force of the magnitude of the force of the spring must be equal to the magnitude of the force of gravity. We can then rearrange this equation to find L0. All of these values were then inputted into our VPython program. We incorporated the energy principle by making our system the spring and the attached mass, and having nothing in the surroundings, therefore no work is being acted on the system from the surroundings. That way there is no change in energy, and all the changes in energy must add up to zero. These were accounted for using the standard equations for kinetic energy, potential gravitational energy, and potential spring energy. The values were then updated through Newton's second law, and the spring was updated using the new L value for each iteration. The value for the change in kinetic and potential energies were also accounted for. We then run our program and we look at the plot of all the changes in energy to see if they satisfy the energy principle. We can also see that our model motion is pretty feasible for what we've seen in the video. When we go back and analyze our energy plot, we can see that the total change in energy, which is represented in yellow, pretty much stays consistently at zero. This is good because it satisfies the energy principle. We can also see that the blue kinetic energy and the green gravitational energy stay consistent as well. We do have one glitch in the potential spring energy, shown here and here. This is an error that we will discuss later, but for the most part we can say that the energy principle is satisfied. We can then run our models side by side to the experimental data, which is shown in red. We can see that the motion is pretty similar, however the position is a little bit off. We see that the models do not match up exactly, but the oscillations do. The x-axis is correct, but there must be an error in the y-axis motion. The most obvious error that could be occurring here has to do with the spring stiffness, which we calculated. It seems that it is too strong. I tried to modify the spring stiffness, however, I found the model to be extremely sensitive to this calculation, and that any change in it would completely change the motion of our model spring. So I decided to stick with the one I calculated, the stiffness that I had calculated, in order to keep the accurate oscillation patterns. This also correlates with the complex motion of a real-life spring in that we are using ideal spring calculations, and these do not always correlate or match up well with a real-life situation. In conclusion, we found that the energy principle is valid in this situation. If there is no energy change in the system, all systems will add up to zero. Newton's second law and the energy principle can also be combined to create a feasible model of real-life motion. However, real spring results will not exactly match up with ideal spring calculations, because there are many more complex interactions and factors that must be accounted for in order to create the most accurate model. Thank you so much for watching.